going to introduce the idea of projective coordinates for points and lines. We already know what points and lines are. Now we want an alternative way of representing them, the way that actually brings them more closely in line with each other, so that points and lines start to look quite similar and the statements we make about them become much more symmetric. There are a lot of other advantages to this projective, somewhat larger point of view, including the fact that allows us to work with fractions a little bit more smoothly. Actually allows us to remove denominators more efficiently, so replace fractional thinking with integer thinking. And it's also turned out to have advantages when we work with a point at infinity and sort of perspective. But it's not gonna play a major role for us, at least initially. The idea is that there is affine geometry and there is projective geometry. Without worrying too much about what projective geometry is, we are going to take just some key ideas from it. So what we're gonna do? We are going to take two ideas that we currently have of points and lines in affine geometry and look at the corresponding way of representing those objects in projective geometry. So how does it go? If we have a point A, which is xy in affine geometry, we can rewrite it as a projective point by considering a proportion 1 to x to y, enclosed in square brackets. And the square brackets are still alerting us that we have a point. But instead of having two numbers separated by a comma, we have three numbers which are forming a proportion 1 to x to y. And now, what about a line? Here's line L in equation form that we have been introduced it as an equation ax plus by equals c. And we have said that this equation is going to be unchanged when we say multiply all of the entries by some number. It's very suggestive of having a proportion, in fact, and suggests to us that we should really be thinking about proportion of these three numbers rather than those three numbers themselves. So we are going to do that, but at the same time we are going to do a slight twist. We're going to move this c to the left hand side, so think about this equation as minus c plus ax plus by equals 0. Before we proceed, please pay attention to the order of the terms here. In this course it will be an agreement that we write the constant term first and the other terms in such order that the power of variables are increasing. You will feel convenience of this agreement when we have quadratic, cubic expressions, high-degree polynomials, and even series in this course. So, if we think about this that way, we can encode it by these three coefficients, minus c to a to b. And that is now proportion. And we enclosing that proportion in round brackets to alert us to the idea that this is a line, not a point. Points in square brackets, lines in round brackets. Okay, let's give an example. This is a classical affine point, 1/3 4/5. According to this, we can rewrite it as a projective coordinates as 1 to 1/3 to 4/5. We have made agreement that these things equal to each other. This is a convention that we adopting. But now, because this is a proportion, we are allowed to multiply the numbers here by anything that we wanted. And the proportion is not going to change. In particular, we can multiply by this common multiple of the denominators here. So we can multiply by 15, essentially clearing these fractions. So we multiply all three entries by 15. We're gonna get 15 to 5 to 12. So this first coordinate that we're introducing, which you may think is kind of waste of time, actually performs the useful role. That it's a place where we can clear denominators for. So starting with the rational numbers, multiplying by the least common multiple of the denominators, we get 3 integers. This is a powerful computational device, because most of us prefer to work with integers rather than with fractions. But they still contain the same amount of information. If you want to go backwards from the proportional point of view toward the point, that we have just to do is divide by this first entry. Then it becomes 1, and these two become these two fractions which determine the point. Let's have a look at an example of a line. For the line L, which is minus 7x plus 2y equals 4. Well, if we bring that 4 to the other side, it becomes minus 4, and then we can represent this line by the proportion minus 4 to minus 7 to 2. All in round brackets, alerting us to the fact that this is a line, not a point. And now, once we have done this, we could, if we feel like it, multiply this proportion by any number that we want to, including minus 1. To rewrite it perhaps slightly in a more nicer way, as 4 to 7 to minus 2. There is another example of a line M, which is in the form y equals 3 over 2 x minus 5. This is not exactly the standard form, that the same way we had here. So let's think about how we can rewrite this in standard form. Well, we can multiply everything by 2 to get rid of this denominator, to get 2y equals 3x minus 5. And then we bring everything to one side to get minus 10 plus 3x minus 2y equals 0. Once we have this form, we can immediately write down what is our projective form of this line is. It is 3 coefficients. The constant term is minus 10, the coefficient of x is 3, and the coefficient of y is minus 2. I hope you can appreciate that there is something powerful about this point of view, because when we're talking about equation of line, it was a little bit ambiguous, right? There are all these different possible ways of rewriting this equation. Maybe with y on the left hand side, maybe with x on the left hand side, or with both of them on the left hand side. But when we convert to this projective form, then these ambiguities mostly disappear. And the only ambiguity that is left is the fact that we can multiply all 3 numbers by a scalar, a non-zero scalar. So conceptually, this is actually a very nice and interactive way of thinking about points, what points and lines are. We could have started by defining affine points and lines in this way, but we prefer to think about points and lines in this more traditional way, and just think about this as being alternative way of representing them. So these are the projective ways of representing points and lines. Okay, so here we come to important formula called the projective incidence formula. From our point of view, we are very interested in formulas. This course will be full of interesting formulas, and think of formulas as being just as important as theorems generally. And if we can, we want to present information in the form of formulas. We feel a little bit more comfortable and confident about validating and interpreting and verifying formulas. Okay, so this is the way of thinking about incidence relationship between points and lines in the language of projective coordinates. And the statement is that the point A, let's say A to B to C, that's the projective form of the point, is incident with the line L, which is R to S to T. That's the projective form of the line, precisely when this relation is satisfied. That is A times R plus B times S plus C times T equals 0. In other words, if we take definition of incidence that we originally have in affine case and convert it into this projective setting, then this is the relationship that we end up with. This is the test about whether this point and this line are incident. So for example, we can check that the point 4 minus 3 lies on the line 3x plus 2y equals 6. We can do that directly, just by substituting this in and see if it works. 3 times 4 plus 2 times minus 3, yes, that's actually equals 6. So yes, this point does lie on the line, this line. But now we can also do this using projective coordinates. Let's see how that would work. So this point would be represented projectively as the point 1 to 4 to minus 3. That's how we go from point in affine coordinates to projective coordinates. This line to be represented by the projective coordinates minus 6 to 3 to 2. Okay, and then we can check incidence just by applying this rule. 1 times minus 6 plus 4 times 3 plus minus 3 times 2 equals, that's minus 6, that's 12, that's minus 6, so yes, we get 0. We get 0, so yes, this point and this line are incident. That's how we check that relation in projective coordinates. So next I'm going to show you two very important formulas that allows us to do two fundamental things we want to do. First of all, just to find the join of 2 points. We have 2 points, how to find the equation of a line that's joined them. And then secondly, how to find the mid of 2 lines. And I'm going to see that this projective point of view really makes these problems very interesting and attractive. Okay, so the join of the points A and B, and the point A is A to B to C, and the point B is D to E to F. This is the following line, L, which we're gonna first of all write as AB. So AB means the line that joins AB, the line that passes through A and B. And here is the formula for it, projective coordinate wise. So you see this by these round brackets, and there are 3 entries. And the entries are what? The entries are BF minus CE, that's the first entry. The second entry is CD minus AF. And the third entry is AE minus BD. That might look like a rather imposing formula, but I do remind you that those are exactly the kind of quantities that appeared when we were investigating the question when a given 3 proportion equals another 3 proportion. So this thing here is just the second and third entries here, here and here. So we just look at BC and AF, so this is B times F minus C times E. And the second entry just involves the first and third entry of both. So this is C times D minus A times F. And the third entry just involves the 2 first entries here. So this is A times E minus B times D. So for example, if A is a point 3, 1 and B is a point minus 1, 4, here's the diagram. There's a point A, 3, 1, and a point B, which is minus 1, 4. Then we might want to find the equation of the line L passes through these 2 points. In high school, you may have learned that in order to solve this, you need to solve some system of two linear equations. This is the alternate way and very powerful way of solving this important problem. What we do, we convert the points into projective coordinates. So 3, 1 becomes 1, 2, 3 to 1, and minus 1, 4 becomes 1, 2, minus 1, 2, 4. And then we just apply this formula to write down immediately the projective equation of the line passes through these 2 points, which is what? Okay, so the first entry is obtained by looking at the second and third entries here. So 3 times 4 minus 1 times minus 1. The second entry is obtained by looking at the first and third entries here. It's 1 times 1 minus 1 times 4. And the third entry is obtained by looking at the first 2 entries here. It's 1 times minus 1 minus 3 times 1. And that amounts to 3 times 4 minus 1 times minus 1. This is 12 plus 1. This is 13. The second entry is 1 times 1 minus 4. It's minus 3. And 1 times minus 1 minus 3 is minus 4. So we get 13 to minus 3 to minus 4. Now if we can multiply this proportion by minus 1, we get minus 13 to 3 to 4. And then the equation of this line must be minus 13 plus 3x plus 4y, or this is 3x plus 4y equals 13. And just to check, let's just check that the point 3, 1 satisfies this line. That is 3 times 3, that's 9, plus 4, yes, that's 13. And when we plug in minus 1, 4, we plug in minus 1 here and 4 there, we get minus 3 plus 16, yes, that's 13 as well. So this is indeed the equation of the line that passes through those 2 points. So we can solve the bunch of high school algebra problems by just remembering this particular formula here. It's a very important formula about how to find the join of 2 points in projective coordinates. So there is a dual problem, the very similar kind of problem to ask if you have 2 lines, say L and M, how to find the point which lies on both of them. So this is of meet of lines formula. The meet of the lines L, let's say the line is A to B to C in projective coordinates, and M, which is say D to E to F, also in projective coordinates, is the point A, and we write LM to represent that this is the meet of 2 lines L and M, and it's given by this formula in square brackets, and there are 3 quantities, and these quantities are exactly the same quantities as appeared in previous formula. So if you memorize previous formula, you automatically know this one. Just remember that output is the point, therefore we write it in square brackets. So for example, here are 2 lines that we looked at earlier. The line L, which is 3x plus 2y equals 6, and the line M with the equation x minus y equals 1, and we'll be interested in where these 2 lines meet. In projective coordinates, the lines are minus 6 to 3 to 2. This is the line L. What about M? It's a line minus 1 to 1 to minus 1. So here are the projective coordinates of these 2 lines. Now we're applying this formula. So there are 3 components. The first one involves the second and the third entries of these 3 proportions. So 3 times minus 1 minus 2 times 1 is here. Then middle entry is obtained from the first and third entries. So it's 2 minus 1 minus minus 6 times minus 1. And the third entry is obtained by from the first and the second entry here. So it's minus 6 times 1, minus 3 times minus 1. And what we get is minus 3 minus 2 is minus 5, minus 2 minus 6 is minus 8, minus 6 plus 3 is minus 3. And we're allowed to multiply, say, by minus 1. So we get 5 to 8 to 3. Now if we want to convert that point from projective coordinates to affine coordinates, the best thing is to do is divide by this first entry. So we get 1 here. When we divide by 5 everything, we get 1 to 8 over 5 to 3 over 5. That's the way we can read of what the coordinates are. So 8/5 and 3/5. 8/5 here and 3/5 here. So notice that with this projective point of view, these two problems of finding the line that goes through 2 points and the point line to lines, these are essentially exactly the same problems. That we get kind of duality, similarity between points and lines that was completely invisible to us from a affine point of view. So that's a powerful kind of orientation and will be useful for us. So we've learned a lot in this lecture. I remind you that this lecture is complemented by a lot of extra information on the course. There are more material given in details and justified some theorems, formulas that we talked about, a lot of work examples and problems for you to tackle with a range of difficulties, and some even more advanced problems occasionally. So there are a lot to do, and it's a great subject. So I hope you enjoyed this lecture in the Algebraic Calculus. I'm Anna Tomskova. Thanks for listening.